Imagine a scene of near total devastation. It is London, 1940. A street, once lined with neat brick houses, is now a portrait of chaos. In the center of this destruction, there's a mangled arch of corrugated steel looking like a crushed tin can. The house it once sat behind is simply gone, erased from existence, leaving behind only a crater and a scattering of splinters. But here's the paradox. The family that was huddled inside this humble metal shell, though undoubtedly shaken and terrified, survived the blast. They lived. Now, fast forward 80 years. Picture a modern American subdivision in the aftermath of a powerful hurricane. Where a brand new house once stood, there is now only a foundation slab, wiped clean, as if by an angry god. The possessions, memories, and very structure of a family's life have been torn apart and scattered across a field of debris. The occupants, if they were inside, faced unimaginable peril. Yet, how is this possible? How can a simple, almost primitive structure of steel and dirt, hastily constructed 80 years ago in the crucible of a world war, so decisively outperform a brand new, code-compliant 21st century home? The question is as unsettling as it is profound, and the answer is not found in magic or chance. It is found in the unyielding laws of physics. It is a story about the staggering cost of forgotten wisdom, the danger of misplaced priorities, and a potentially fatal flaw in how we have come to think about the very buildings we trust to keep us safe. The secret to survival lies buried in the past, a hidden genius we have systematically sacrificed for the sake of cost, convenience, and curb appeal. Before we excavate this forgotten science, type "built to survive" in the comments if you believe our society has come to prioritize the appearance of safety over the reality of it. I am genuinely curious to know, does this disturbing paradox resonate with you? Number 1, the weaponization of the city. To truly grasp the genius of the solution, we must first confront the sheer, unmitigated terror of the problem. Picture London, starting on September 7th, 1940. This was the beginning of the Blitz, a German bombing campaign that lasted for 8 brutal months. This wasn't merely conventional warfare. It was the systematic weaponization of architecture, a horrifying strategy designed to turn the sprawling metropolis of London against itself. The psychological goal was as important as the physical one: to shatter civilian morale and force a surrender. The threat arrived from the sky in 2 primary, devastating forms. First, the high explosive bombs. These were instruments of pure concussive force, engineered to create a cataclysmic blast wave that could pancake buildings, instantly transforming brick, timber, and glass into a storm of deadly projectiles. The shock wave alone, an invisible tsunami of pressure, could ripple through the urban landscape, turning structures blocks away into piles of rubble. A single bomb could erase a building, but its shock wave could kill and maim from a distance, making nowhere feel safe. Then, as the city reeled from the explosions, came the incendiaries. These weren't single large bombs, but thousands of small thermite devices, scattered like deadly seeds across acres of rooftops. Their purpose was not just to destroy a single point, but to ignite a firestorm, a terrifying, self-sustaining vortex of flame that could achieve temperatures high enough to melt steel and consume entire districts. London, with its dense network of aging buildings, was a veritable tinderbox. The nightly raids created a landscape of hell, with skies lit orange by raging fires, and the air filled with the constant drone of bombers, the scream of falling ordnance, and the crash of collapsing buildings. The scale of the destruction was immense, with 2 million houses damaged or destroyed across the UK, 60% of them in London. This was a new kind of war, where the front line was no longer a muddy trench, but every civilian's doorstep. Number 2, the failure of conventional wisdom. In the face of this unprecedented aerial onslaught, the initial government response was tragically and fatally flawed. Officials, operating on the conventional engineering wisdom of the time, commissioned the construction of communal street shelters. Built from thick brick walls and topped with heavy concrete roofs, they certainly looked sturdy. They projected an image of strength and permanence, designed to reassure a terrified populace. But this appearance of safety was a deadly illusion. When a high explosive bomb detonated nearby, the immense blast wave would strike these rigid structures with unimaginable force. The brittle brick walls, unable to flex or absorb the energy, would shake violently and shatter into countless pieces. The heavy concrete roof, its support suddenly gone, would then collapse downwards, crushing everyone huddled inside. It was a brutal, repeated lesson in structural physics. Brute strength is not enough. In the face of explosive forces, rigidity can become a death sentence. As the failures of these shelters became terrifyingly clear, people grew desperate. Rumors of their unreliability spread, and they became deeply unpopular. A profound sense of distrust in official solutions took hold, and thousands began to flock to the London Underground, intuitively recognizing that depth offered a degree of safety that surface structures could not. Initially, the government resisted this mass movement, fearing it would interfere with transport and that people might not want to leave. But the will of the people prevailed. Faced with crowds who simply bought tickets and refused to leave, the government eventually had to relent, officially sanctioning the use of the tube. Over the course of the war, they fitted out 79 stations with bunks, first aid posts, and canteens, turning the city's transport network into a vast subterranean sanctuary for an estimated 170,000 people. Yet, the tube could not save everyone. It was a solution primarily for those in central London. For the millions living in the sprawling suburbs, most of whom did not have basements, it was not an option. They needed a solution that was cheap, could be mass-produced on an industrial scale, and crucially, could be installed in a typical backyard. The challenge was monumental. The answer, when it came, would not be found in building thicker, stronger walls, but in a revolutionary yet profoundly simple piece of forgotten genius. Number 3, the People's Shield. Sir John Anderson's challenge. The daunting task of protecting millions of suburban families fell to Sir John Anderson, the Minister of Home Security. Anderson was not a typical politician. He was a scientist by training, and he approached the problem with a scientist's mind. He understood that the challenge wasn't about trying to create an indestructible fortress capable of stopping a direct bomb hit, an impractical and costly fantasy. The real problem was about surviving a bomb's devastating effects. The blast wave and the lethal shrapnel. The solution that emerged from this shift in thinking was one of the most effective and ingenious pieces of civil defense engineering in history, the Anderson Shelter, designed in 1938 by William Patterson and Oscar Carrison at Anderson's request. It was a marvel of practicality and physics. The shelter was delivered to homes as a self-assembly kit composed of 14 panels of corrugated steel. This was a deliberate strategy of mass production and distribution, aimed at empowering ordinary people to protect themselves. Over 3.6 million Anderson shelters were produced, with production peaking at 50,000 units per week at factories like the John Summers and Sons Iron Works. In a profoundly democratic move, the government provided these shelters free of charge to all lower-income families, those earning less than £5 per week, while those with higher incomes could purchase one for a modest £7. This was, in effect, a democratic shield for the people, a national policy acknowledging that every family deserved a chance at survival. From the outside, a properly installed Anderson shelter looked rather humble, like a garden shed that had decided to become a hobbit hole. It was designed to be sunk 3 to 4 feet into the ground, with the excavated dirt then piled high over the top and sides. Yet, its simple, almost primitive appearance hid a profound and revolutionary understanding of physics that would save countless lives. Number 4, the science of survival, ductility, and earth. The Anderson shelter's incredible success was rooted in 2 fundamental principles: ductility and the strategic use of earth cover. These were not complex, high-tech solutions, but rather an elegant application of basic physics, turning the bomb's own energy against itself. First, and most important, was the principle of ductility. To understand ductility, think of it as the polar opposite of brittleness. A brick or a piece of unreinforced concrete is brittle. When it is pushed past its structural limit, it doesn't bend, it shatters catastrophically. The steel used in the Anderson shelter, however, was ductile. When a material like steel is pushed past its limit, it doesn't break apart. It stretches, it deforms, it bends. This process, known in engineering as plastic deformation, is a phenomenal way to absorb energy. The shelter was explicitly designed to do this. When the immense, instantaneous pressure of a bomb's shockwave hit it, the curved, corrugated steel panels were engineered to flex, buckle, and groan. They would become mangled and distorted, but they would not shatter. The blast's destructive energy was spent in the act of bending the metal rather than being transferred to the occupants inside. It was the equivalent of a judo master redirecting the force of a charging opponent. The shelter was intelligently designed to fail gracefully, becoming permanently deformed, but remaining structurally intact. A protective cocoon amidst the chaos. The second principle was the simple, brilliant use of the earth itself. The instructions for assembly were very specific. Sink the shelter 4 feet into the ground and cover the roof with at least 15 inches of the excavated soil. This thick layer of earth served as a massive natural shock absorber. It dissipated the incoming blast wave before it could even reach the steel, significantly dampening its force. Furthermore, this earth cover provided incredible protection against shrapnel and debris, which were responsible for a vast number of casualties during the Blitz. The shelters were by no means perfect. They were often cold, cramped, and prone to flooding in low-lying areas. But they worked. A November 1940 survey found that while only 27% of Londoners were using them at the time, they were remarkably effective at saving lives on an industrial scale. Number 5, the shelter within. Herbert Morrison's cage. The Anderson shelter was a triumph, but it had one significant limitation. It required a garden, a patch of earth to be buried in. This left a massive gap in protection for the millions of people living in dense urban terraces or apartment blocks, with no access to private outdoor space. A new solution was needed, one that could protect a family not from a collapsing garden, but from their own house collapsing around them. This new challenge was taken up by the new Home Secretary, Herbert Morrison, and a brilliant engineer named John Baker. Baker, a pioneer in the field of plastic theory for steel structures, conceived of a shelter that operated on a completely different premise. If you couldn't get out of the house, this was designed to help you survive the house caving in on top of you. The result was the Morrison shelter, essentially a super strong steel cage. Officially called the Table Morrison Indoor Shelter, it was ingeniously designed to double as a household dining table, making it a practical addition to a cramped home rather than a disruptive one. Like the Anderson shelter, it was delivered as a self-assembly kit. This one, with 359 parts and could be bolted together by the householder. By the end of 1941, 500,000 of these life-saving tables had been distributed, with another 100,000 added in 1943 in preparation for the V-1 flying bomb attacks. The Morrison shelter's genius lay in its direct application of Baker's work on plastic deformation. The thick steel plate on top and the sturdy steel frame were not designed to be perfectly rigid. They were designed to strategically bend under the immense weight of tons of falling rubble from a collapsing upper floor. As the steel top deformed, it would absorb the kinetic energy of the collapse, dissipating the force and protecting the space underneath. A post-war survey of 44 severely bomb-damaged houses produced astonishing results. Of 136 people who had been sheltering in correctly placed Morrison shelters, 120 survived with only slight or no injuries. In one documented case, a single shelter withstood the crushing weight of 1.5 tons of rubble with no obvious distortion, saving the 5 people who were inside. These shelters weren't about creating an immovable object. They were about creating an intelligent system that could absorb and safely dissipate catastrophic energy. Number 7. The disassembled home. Tornadoes and earthquakes. The fragility of the modern home is further exposed when confronted by the unique forces of tornadoes and earthquakes. A tornado is not just a straight-line wind, it's a vortex that combines extreme rotational winds, powerful updrafts, and a sudden, dramatic drop in barometric pressure. It seeks out and exploits every single weakness in a structure. Forensic engineering after tornadoes consistently reveals that a primary failure point is where the walls meet the foundation. The house is often ripped from its base because the anchor bolts connecting the wooden wall plates to the concrete foundation are too small, spaced too far apart, or are missing crucial plate washers that prevent them from pulling through the wood under extreme tension. A modern wood frame house is supposed to function as a unified system, with what engineers call a continuous load path. This is an unbroken chain of strong connections designed to transfer forces from the point of impact, like wind hitting the roof, down through the walls, into the foundation, and safely into the ground. If you break any single link in that chain, a weak roof-to-wall connection, an improperly bolted wall-to-foundation connection, the entire system fails. The house doesn't just collapse, it effectively disintegrates into its component parts. Finally, let's consider the earthquake. An earthquake attacks a building from its base with violent lateral shaking. Here, our modern material choices can become a deadly liability. Rigid, brittle materials like unreinforced brick and concrete block, common in many parts of the world, are incredibly dangerous in seismic zones. They possess high compressive strength. They are strong when you push down on them, but have almost no tensile strength. They cannot stretch or bend. When shaken violently, they don't flex. They crack and shatter, leading to a sudden, total collapse. This is the direct fatal opposite of the ductility principle that made the World War II shelters so effective. The core flaw is this: we build beautiful, complex systems optimized for fair weather. We use lightweight materials for construction speed, create vast open-plan designs for aesthetic appeal, and assemble a series of components that often lack the robust connections needed to act as a single, unified, resilient structure. We have forgotten the fundamental lesson of the Blitz. It is not brute strength that saves you. It is the ability to absorb energy. It is the wisdom to bend so you do not break. Number 8. Echoes of the past. Resilient design. Today. But it doesn't have to be this way. The very same principles of survival, forged in the fires of war, are not lost to history. They are being rediscovered, rebranded, and deployed in some of the most advanced and resilient construction projects today. The technology is here, and the historical precedent is undeniable. The core principle of the Anderson shelter, ductility and energy absorption, is alive and well in the form of modern seismic dampers. In earthquake-prone regions, large buildings are now designed with massive internal shock absorbers. These devices, which can be based on friction, viscous fluids, or yielding metal components, are designed to move and counteract the violent swaying of an earthquake, absorbing its kinetic energy and dissipating it as heat. This prevents the energy from being transferred to the building's primary structure, protecting it from catastrophic failure. It is the exact same philosophy as the Anderson shelter's flexible steel, just scaled up for a skyscraper. The genius of the Morrison shelter, the concept of a reinforced core, has a direct modern descendant, the tornado safe room. A safe room, as defined by FEMA, is essentially a structurally independent box, typically built from reinforced concrete or steel, often located within a closet, bathroom, or garage of a larger home. It is securely anchored to the building's foundation and has been tested to withstand the impact of debris traveling at speeds of over 250 miles per hour. The design philosophy implicitly acknowledges that the main house might be lost in an extreme tornado, but that the people inside the core can be saved. The house is disposable. The core is what matters, a direct echo of John Baker's life-saving cage. Even the principle of using the environment, exemplified by the Anderson shelter's crucial earth cover, is being reborn in the form of modern earth-sheltered homes. By building a home directly into a hillside, or covering it with a thick layer of soil, you gain immense free protection from high winds and fire, not to mention incredible energy efficiency. It is the ultimate expression of working with nature to achieve safety. Finally, the principle of mass production, which made the World War II shelters so successful in their widespread deployment, is now echoed in the rise of high-performance, prefabricated and modular construction, where homes built to exacting, resilient standards in a factory can be deployed quickly and more affordably. Number 9, a choice of resilience, the forgotten legacy. More than 80 years ago, under a sky filled with fire and the constant threat of annihilation, a generation of ordinary people learned a series of hard and unforgettable lessons about what it truly means to survive. They learned through terrifying trial and error that resilience didn't come from rigid, unyielding walls that would shatter under pressure. It came from the quiet, unassuming genius of a curved piece of corrugated steel that knew how to bend without breaking. It came from a humble steel table that could accept the crushing weight of a collapsing world and hold it at bay, protecting the family huddled beneath. The World War II shelters worked because they were designed with a singular, unambiguous purpose: to survive catastrophic forces. They were not designed for curb appeal or to maximize square footage. They were designed to endure. They masterfully employed principles of ductility, plastic deformation, and energy absorption that are as valid and vital today as they were in 1940. Our modern homes, in stark contrast, often fail because they are designed for a world of predictable, gentle weather that science tells us no longer exists. They are meticulously optimized for construction cost and aesthetic trends, while genuine resilience is often treated as a dangerous afterthought or a luxury add-on. We have, in many ways, traded the robust, hard-won wisdom of our grandparents for a fragile, superficial beauty. But those critical lessons are not lost. They are waiting for us, baked into the very history of engineering, embedded in the properties of earth and steel. They are holding the key not just to building safer houses, but to cultivating a more resilient society. The past still has urgent lessons to teach, and together we can work to keep them alive. We've only begun to scratch the surface here. What are your thoughts on modern construction practices and the trade-offs we routinely make between cost and safety? Do you know of any historical shelters like the Anderson or Morrison still standing in your area? Share your thoughts and stories in the comments below. And if you find this exploration of real survival history and forgotten engineering as compelling as we do, please share this video with someone who needs to see it. Thanks for watching. Number 9, a choice of resilience. The forgotten legacy. More than 80 years ago, under a sky filled with fire and the constant threat of annihilation, a generation of ordinary people learned a series of hard and unforgettable lessons about what it truly means to survive. They learned, through terrifying trial and error, that resilience didn't come from rigid, unyielding walls that would shatter under pressure. It came from the quiet, unassuming genius of a curved piece of corrugated steel that knew how to bend without breaking. It came from a humble steel table that could accept the crushing weight of a collapsing world and hold it at bay, protecting the family huddled beneath. The World War II shelters worked because they were designed with a singular, unambiguous purpose: to survive catastrophic forces. They were not designed for curb appeal or to maximize square footage. They were designed to endure. They masterfully employed principles of ductility, plastic deformation, and energy absorption that are as valid and vital today as they were in 1940. Our modern homes, in stark contrast, often fail because they are designed for a world of predictable, gentle weather that science tells us no longer exists. They are meticulously optimized for construction cost and aesthetic trends, while genuine resilience is often treated as a dangerous afterthought or a luxury add-on. We have, in many ways, traded the robust, hard-won wisdom of our grandparents for a fragile, superficial beauty. But those critical lessons are not lost. They are waiting for us, baked into the very history of engineering, embedded in the properties of earth and steel. They are holding the key not just to building safer houses, but to cultivating a more resilient society. The past still has urgent lessons to teach, and together we can work to keep them alive. We've only begun to scratch the surface here. What are your thoughts on modern construction practices and the trade-offs we routinely make between cost and safety? Do you know of any historical shelters like the Anderson or Morrison still standing in your area? Share your thoughts and stories in the comments below. And if you find this exploration of real survival history and forgotten engineering as compelling as we do, please share this video with someone who needs to see it. Thanks for watching.